All right, so last set of notes for the rest of the year today over nuclear reactions, and so that's going to cover the general reactions as well as fission and fusion. So first off, nuclear reactions are anything where the reaction takes place when two nuclei or at least two nucleons hit each other. And again, this is different from chemical reactions because with a chemical reaction, it's the electrons of an atom that are interacting with each other. But in this case, we're looking at the nucleons. So the important thing to remember is that regardless of what we have going on, so whether they're small atoms, big atoms, one atom, two atoms, whatever's happening, a few things have to be conserved. Electrical charge, nucleon number, mass energy, those are the three things that we're going to focus on. But then also linear momentum, so some applications of it is important. So if something's sitting still, one thing jets off to the left, the other thing has to jet off to the right, or whatever direction it has to be. But that has to be conserved, as well as angular momentum too. So all of those things have to be conserved within a nuclear reaction. So in general, we're going to write a reaction as A plus X goes to B plus Y, where A and B are real small particles, so things like neutrons, electrons, stuff like that. And then X and Y are going to be actual full-fledged atoms or nuclei. And so if we want to figure out how much energy is gained, lost, whatever it happens to be in a reaction, we know that the change in energy is equal to our change in mass multiplied by c squared. And so what we've got here is the sum of our initial masses and then subtracting the final masses of the objects to figure out that energy. And so normally we would do delta M, where it would be final minus initial, but in this case we have it as initial minus final, so that our Q comes out to be a positive value. Because if this is the case, whenever we've gotten some products that are less massive, that means that energy has been created. And so if energy is being created in AP Physics land, we're going to call that a positive value. And so we have to have that positive value for Q come out if we've lost mass. So that's why it has to be switched from normal. So we do initial minus final if we're just looking at the masses multiplied by c squared, and that gives us the amount of energy. But if we want to look at it in terms of kinetic energy, so how much those atoms are actually moving, then we need to do the normal final minus initial setup, because even though the products are going to have less mass, we also know that that means that there's more energy, because that mass energy ratio has to be conserved. And so again, if we want something to show up as having a positive, we need to have it arranged so that our final here is what we start with, and then we subtract away the initial amounts of energy. So whichever way you do it, it's totally fine. It just depends on what the problem's asking for and all that good stuff. But regardless of how you go about it, if Q comes out to be positive, that means that the products have more kinetic energy, or that they're less massive. So therefore, energy has been released in the reaction, and that's going to be exothermic. Whereas if Q is negative, so that means that the products either have less energy and or that they are more massive than the initial ones, meaning that energy had to go, or more energy had to go into the atoms than was released. So that's going to be endothermic, where energy was absorbed. And then another key term is going to be threshold energy. And so that's the minimum kinetic energy between the reactants required to get it to occur. So regardless of what the output is, you're not going to get that output until you have at least that minimum input required in order to even get this stuff started. Kind of like with a lot of chemical reactions like gasoline, if it's just sitting in a can, it's not going to burst into flames. You have to apply heat to it, and more than just hitting it with a hairdryer, maybe like a match or something like that. You have to make sure that there's enough energy to start the thing in order to get it to go. Okay, so if we wanted to go through a problem real quick, it's really pretty self-explanatory, and there's not a whole lot new in this section. So first thing, we've got an equation, and we don't know exactly what's made, so we have to go through and do the math. Well, if we do that, We find out that the bottom is going to be 6, so we know we're dealing with carbon. The top is going to be 13, so it's carbon 13. Then we need to find the mass defect, or how much mass, again, was lost. So because I'm going to be looking at the energy, and again, it is totally up to you which way you want to do it, but we're going to do the initial minus the final just to make everything work out nicely. And so whenever we plug those values in, if we multiply the 7 neutrons by whatever the mass of a neutron is, 6 protons by whatever the mass of a proton is, we get our 13.033. We do the math, and we find out that we have lost negative 0.002207 units of mass. And so when you go to plug that in, we find that there's actually a negative energy of negative 3.294 times 10 to minus 13 joules. And again, you can go through and you can work through the math if you'd like to yourself, but ultimately, because it winds up being negative, that means it's an endothermic process. So more energy was required to make it happen than was released through the reaction. So one of the most common particles to utilize in nuclear reactions are neutrons, and that's because they have no charge. So normally you'd have a problem if you had an electron trying to zip into the nucleus to maybe bond with a proton to have things happen. It's really hard to get through that electron cloud around the atom because the negatives are going to repel, so bad things happen. And it's the same thing with if I tried to do it with a positron or a proton or something like that. Once it gets through the electron cloud, it will wind up being repelled from the nucleus because it's positively charged. So neutrons work really well because they're neutral, so they don't have any of those forces going on. And so by shooting a neutron at particular isotopes of heavy atoms, we can actually make even heavier atoms, or atoms with a larger proton number from that as a result. So uranium-238, which is one of the more stable forms of uranium, if it gets hit with a neutron, it turns into uranium-239, which is unstable, so it's going to decay into neptunium through beta decay. So notice the proton number went up. That's just because a neutron converted into a proton. To balance out the charges, we have to have an electron, and then there's a neutrino going out there for conservation stuff as well. And then neptunium on its own will also beta decay and make plutonium. So we can wind up by just simply adding one thing, we can create more elements directly from that. All right. So calculate the Q of the reaction, state whether more energy is released or not. So essentially what this is you're trying to figure out whether it's exothermic or endothermic. So by going through the math, so it gave us all the numbers there. So that was nice. You didn't have to actually go through and try to do all the multiplication stuff. We find that we wind up with a positive value. So because of that, we know it's exothermic because more energy was released. All right, which is conserved. And that is going to be all of the above. All right, nuclear fission and fusion. So at the beginning, Enrico Fermi and Emilio Segre, I probably pronounced that one wrong, but they were the first ones to really discover this fission stuff, because we knew that nuclear reactions could occur. We knew that if you hit something with neutrons, it could take it on and then it would turn into a new element. And so they were bombarding uranium with neutrons, and they saw that beta particles were coming off of it. And so initially they figured, okay, well, that's because uranium turns into neptunium, which then turns into plutonium. So that's what's happening. But when they did the analysis, they actually found that barium was being formed, which is still it's a big atom, but it's a lot smaller than uranium is. And so whenever they started studying this more and passed it on to Lisa Meitner and Otto Frisch, they actually figured out that not only was barium being formed, but also krypton. And initially we didn't know that it was the barium, or that the krypton was being formed, because that was a gas. And so naturally, whenever it would initially happen, it would just head on out. So now we found this barium and krypton, and then of course when we added them together, we found that, oh hey, that's what essentially the uranium was. And so those particles then decay via beta particle transmission, so that's what was initially observed. So it took about 5 years to figure out what exactly was happening to nuclear fission to figure out that it was a thing. So again, they used neutrons in order to do this, and they bombarded uranium-235 with it. Specifically, they use what are called thermal neutrons. Basically, they move really, really slowly so that when they get by the nucleus, there's a greater chance of it getting sucked in because it's around there for a longer period of time. But what happened was that created an unstable form of uranium and caused it to split into two atoms, which would then go on to beta decay. And so for uranium-235, it doesn't always decay the exact same way. There are a handful of different ones. The two most common are going to be these two down here. So initially, uranium-235 is bombarded with a neutron, which causes it to turn into uranium-236, which on its own is not stable. So it undergoes nuclear fission, and two elemental atoms are formed as a result, and they're always both relatively close in size. Now, I say relatively, you can see that there is a fair difference between them, about 20, but it's not like we make one under uranium and then a hydrogen. They are relatively close together. Then we also get a handful of neutrons. How many just depends on what atoms are involved, and then a certain amount of energy as well. So what winds up happening with this nuclear fission then is whenever those neutrons are released, remember, neutrons are what started the process to begin with. So if those neutrons can find their way to another uranium-235 molecule, then that can pass on to create more neutrons, which can then go to another, more U-235s, and keep going on and on and on and on and on until we're out of uranium. And so this first actually self-sustaining nuclear reaction was built by Enrico Fermi, one of the first guys, in 1942. So it's been around for a good amount of time. Alright, so looking at how we use it today. So in nuclear fission, and you may have seen a diagram like this before. If you have, you can go ahead and skip forward into the video. But anyway, the general way it's set up is we have this reactor vessel, and this is where all the uranium is going to be located. And so within that vessel, those uranium atoms, when they break down, remember, they're releasing neutrons, and they're also releasing a lot of energy. And that energy gets converted into thermal energy or heat. And there's usually some kind of coolant, usually water, that's circulated through the whole thing. And so essentially what happens is that nuclear fuel isn't creating the electricity itself, but it's heating up water, which is then used to create steam to turn a turbine to create the electricity. So it's basically a fancy boiler. And then every nuclear reactor has control rods, which are rods that are made of an element that's specifically designed and chosen to absorb neutrons. So that if you put more control rods into the reactor, that means there's less collisions between neutrons and uranium, so you slow down the reaction, or if you want to speed it up, pull them out so that more neutrons can do their thing. So that says what I was saying before. Then critical mass. So that is the minimum amount of stuff that we need to sustain a nuclear fission reaction. So there is a minimal amount of stuff that you have to have. You can't just get a little bit of uranium, throw it in a reactor and say, okay, that'll react all the way. Because ultimately, if something is too small, because it's all about chances, is that neutron going to come off in just the right trajectory to hit the nucleus of another uranium atom. And so by giving yourself more material to work with, you're going to have a higher chance of getting that probability to occur. And so you've just got to make sure that you have the minimum stuff required. And so whatever that minimum happens to be, it depends on exactly what kind of isotope you're dealing with. It depends on the purity of it, how much stuff in there is actually radioactive, a whole bunch of factors. But there is that minimum threshold that is going to be critical mass. So nuclear reactors are designed so that they have that critical mass at all times, but that it's a slow and sustained release, whereas a nuclear weapon has the same critical mass, but it's designed specifically so that that release happens almost instantaneously. All right, then nuclear fusion. So 1938. So this was before we had actually discovered that fission was a thing that actually happened for sure with uranium. And so this was just somebody postulated an idea, Hans Bethe, that the reason that the sun didn't cool down, because initially it wouldn't make sense before we knew about this mass energy conversion and all this stuff, that the sun would even be sustaining itself, because as something burns through its fuel, it's either got to get smaller or it's got to lose energy. But since we noticed that the sun was not cooling down at all, there had to be something else in play. And so he came up with the idea that hydrogen, which we knew that the sun was mostly composed of, would fuse together in order to create helium. And so nuclear fusion is taking some number of small elements, combining them together to make a bigger one. And if you remember back from one of the previous sets of notes, that chart with the binding energy per nucleon, it's nuclear fusion is going to happen for all of those that are on the positive slope edge of that, because anything that's on the negative slope requires more energy to fuse together than is gotten out from the actual reaction itself. So in the sun, we've got three main different types of reactions that occur. The first two have to happen twice, where two hydrogen 1 atoms are going to fuse together to create a hydrogen 2. A positron and a neutrino are also going to get spat out from that as well. Then that hydrogen 2 and then another hydrogen 1 are going to combine together to make helium 3 and gamma radiation. Then two of the helium 3s, which is why this process has to happen twice, because we have to make two of these guys, creates helium 4 and also two hydrogen 1s. And so the first two don't really create a whole bunch of energy. The first one, not a lot at all. The second one creates a fair amount, mainly because of that gamma. So any of the gamma radiation that's coming from the sun, or at least the vast majority of it, is coming from this reaction here that's happening twice. And then we wind up last with our stable helium 4. And then again, two new hydrogens, so that which will then get recycled into the process to start it over again. And so net-wise, we wind up starting with 4 hydrogens, we end with a helium, 2 positrons, 2 neutrinos, and 2 gamma radiation. And again, really, really big stars that have enough energy can create elements up to iron through this process. But anything bigger than that requires more energy to put in than is gotten out. So that's what triggers the end for stars. So nuclear fusion, one of the big advantages of it is that we get a lot of energy from it, but it also requires a huge amount of energy in order to get it to start. With the sun, it's because there's such high temperatures from the massive amount of gravitational forces compressing the hydrogen gas within the sun. That's what initially started it there. If we try to do a nuclear fusion reactor, we have to, first of all, provide enough energy to get it started, which again is a massive amount. We can do it, and we do it on a regular basis, like whenever we need to, we can. And then it's also better than fusion because the fuel is more plentiful and it produces a lot less radioactive waste because it's essentially nothing. We just have to make sure that anything that gets hit with the gamma radiation is disposed of properly. But as far as actual fuel is concerned, it doesn't create any direct byproducts of radioactive waste. However, the big problem with it is simply that we don't know how to contain it in a way that will be profitable energy-wise. Because while we can get it started, and it takes a huge amount of energy to do that, we're talking about temperatures of the sun here. And so that's, you can't just, put that in a box, because best case scenario, the box is going to melt, let alone potentially vaporize and turn into a gas. So we have to contain everything with magnetic fields. But the things that create the magnetic fields have to be somewhat close to the reaction to happen. So either we put it close enough that we can get the energy, but then those magnetic field generation thingamahoos, whatever they be, they're going to wind up melting and frying, and then bad things happen. The other option then is that we have to have them far enough away to be protected from it, but at that point they have to create an even stronger magnetic field, since magnetic fields weaken over distance, and that's where the problem lies. Alright, which particle is used to strike U-235 to make a chain reaction? And hopefully we know that is a neutron. Process do stars use to emit massive amounts of energy? Again, hopefully we already know. That's going to be fusion. Nuclear fission reactions are going to produce. And so the answer here is going to be A. Daughter nuclei with similar masses, so they're, because remember, they're relatively close to each other. The key term here is the very. They're not going to be very different. So they're going to be similar masses, and then it's neutrons that get spat out, not protons. Alright, and then the major factor preventing development of nuclear fusion reactors, and that is going to be simply trying to contain the plasma. We understand the physics of how it works. There's less radioactive products, and there's not a shortage of reactant material, but it's just hard to contain or keep the reaction contained.